Hey everyone, I am Miss Hu, your physics teacher. And in this video, I'm going to go through an overview of the topic on electromagnetic waves. This topic is both in the IGCSE as well as SPM syllabus. Now, please bear in mind that this video is only going through this topic in general. There's, of course, a lot more to know about the individual concepts and subtopics that are covered within this video. Please feel free to do your own additional research if you'd like to know more. What I'm covering in this video is the general information that you would need to answer questions in your examinations. Right, so what we will be covering in this video is we will be going through the characteristics of electromagnetic waves, the electromagnetic spectrum, as well as the applications and harmful effects of electromagnetic waves. So now, let's go through the characteristics of the electromagnetic waves first. But before we get into that, we need to know what are electromagnetic waves. So if you look at the word electromagnetic, you can see that it comes from two words, electric and magnetic. So essentially, an electromagnetic wave is made up of both an electric and a magnetic field. As the definition written here, it says, an electromagnetic wave is formed when an electric field and a magnetic field oscillate around the same axis. So referring to this diagram here for clearer visualization, the black line here represents the axis of which is basically the direction of travel of this wave. So you can see over here, you've got two fields that are oscillating perpendicular to each other. You've got one wave going up and down, and one wave moving left and right. So one wave is electric and one wave is magnetic. Which one is which? It doesn't matter. But you can see that based on this diagram, both of these are oscillating around the same axis. Now, as these fields propagate, they carry momentum and electromagnetic radiant energy. Here's a video to give you a clearer idea of how these waves are oscillating as they propagate in the same direction. So you can see in this video here, you've got the red field that's oscillating up and down, while the blue field is oscillating left and right, and they're both oscillating around the same axis here, which is the direction of propagation. Based on this video, the red field going up and down is the electric field, while the blue field, which is going left and right, is the magnetic field. But honestly, if you just recall, right, okay, it doesn't matter whether up or down, left or right is magnetic or electric, it doesn't matter. Sometimes it's one, sometimes it's the other. They could be changing. It's the combination of both these fields together that make up the electromagnetic wave. What are the characteristics of electromagnetic waves? So as you saw from the diagram and the video just now, electromagnetic waves are actually transverse waves. Now they also travel at the same speed in vacuum. And if you look at the number, doesn't it look familiar? That's the speed of light, correct? Speed of light in vacuum is 3 times 10 to the power of 8 meters per second. And that's pretty much the same speed of the electromagnetic waves in vacuum as well. Now, electromagnetic waves, they may consist of electrical and magnetic fields, but that doesn't mean that they carry any charges or any polarity. So because they have both sides, could be both positive and negative, both north and south, and basically the combination of all that makes them neutral. That's why electromagnetic waves are electrically and magnetically neutral. Just like light, they also do not need a medium to travel, which means that they can travel through a vacuum. So if you recall, like, okay, this looks like light, right? So light can travel through space, which doesn't have any air particles, right? No medium at all. So light can travel through vacuum from the sun to Earth. And that's pretty much the characteristics of electromagnetic waves as well. So, like the cosmic rays that travel through outer space, actually, they're all electromagnetic waves as well. So one way to help you remember the characteristics of electromagnetic waves is to recall the characteristics of light. And the reason why light and electromagnetic waves seem to have so many similar characteristics is because light is actually one of the electromagnetic waves in the spectrum, as you will see on the next slide in the electromagnetic spectrum. All right, so one way to remember these characteristics, remember characteristics of light. They're the same as the characteristics of the electromagnetic waves. Here's a diagram, very pretty diagram that I found on Google. All right, this shows us the electromagnetic spectrum. Now, you do need to memorize the electromagnetic spectrum in the correct sequence, whether you're taking IGCSE or SPM. So you can see here in the middle, this is the spectrum that's listed out. We have radio waves, microwave, infrared, the visible light spectrum, ultraviolet, X-rays, and gamma rays. If you're wondering, how come the word microwave is written in a different font? Well, that's because I added it. The original diagram did not have the word microwave. So if you're wondering why the word microwave wasn't included in the first place, it's because actually, based on older syllabus, microwaves were not listed. In fact, they only learned radio waves, then straight to infrared and visible light, ultraviolet, X-rays, and gamma rays. And the reason for that is because microwaves were classified under radio waves. Microwaves are actually just high frequency radio waves. But in recent years, microwaves have been given their own spot in the electromagnetic spectrum because they have a lot of applications that are unique to microwaves and not to the rest of the radio waves. So yay, leveled up. It's now been given its own spot in the spectrum, and that means you have to memorize that in the correct sequence too, all right? So this diagram is pretty cool because on the top here, it shows us the general uses of each of these waves. So you've got some of the uses of radio waves written here: the broadcasting, radar for microwave, infrared is the TV remote, light bulb for visible light, and also the sun. The sun also produces ultraviolet rays. You got X-ray machine for X-rays, and gamma rays are found in radioactive elements. So we'll cover this in more detail in the coming slides. All right, don't mind some of the spelling errors over here. Oops. All right, let's look at the numbers at the bottom here. What I want you to just take a look, why I included this diagram is because this is a pretty neat diagram. It shows us it helps us visualize the wavelength. So the green numbers over here are actually the wavelengths of the, well, not the wavelength of it's the average wavelength of the individual waves. So starting from radio waves, it's written here about 100 meters. Actually, it's a lot bigger than this, but just to give you visualization, let's say even if it starts from 100 meters, 100 meters is like roughly the size of a building. So basically one wavelength of a radio wave can be the size of a building or even larger, actually. As we move across to the gamma rays, you can see the numbers here are getting smaller and smaller. Right? And when we get to the gamma rays, the wavelength of the gamma rays is so tiny, it's about 0.0001 nanometers. That's about the size of an atom. That's how small it is. Now, let's take a look at the next slide. This slide also has the electromagnetic spectrum, which is another diagram that I found. And for this particular diagram, though, it's listed slightly differently, but you can see for the most part, the waves are pretty much the same. Now, if you're wondering on the left-hand side, what are all these numbers? What's ELF? Actually, right, this is the frequency. So LF is low frequency, then very low frequency, extra low frequency. All of these are actually radio waves. Now, you don't need to know the spectrum to this level, so let's just focus on radio waves in general. So these are all the radio waves. Then we've got microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. So let's look at the numbers at the bottom first. You can see here we've got frequency and wavelength. Just going to move this out of the way so that the numbers are more visible. You can see here the frequency as we start from radio wave and move across to gamma rays. The frequency is increasing. So it starts from 50 hertz, moving up to 1 megahertz, and so on and so forth. The numbers are actually getting larger and larger and larger until it's roughly about 30 exahertz on the side of gamma rays. The wavelength, on the other hand, starts from a huge number of about 6,000 kilometers. So that's why earlier I mentioned actually the wavelength is for radio waves are much, much larger than 100 meters. So they do start from about 6,000 kilometers. And as we move across, you can see how the numbers are getting smaller and smaller and smaller. And when you get to the gamma rays, it's about 10 picometers. So the frequency and wavelengths for the electromagnetic waves in the spectrum are changing. The frequency increases while the wavelength decreases as we move from the radio waves to the gamma rays. So one way to help you remember that, let me move my face back down because I want you to see this. right? So if you know the wave equation of v equals f lambda, if you recall, v is speed, f is frequency, and lambda is wavelength. We already know that all electromagnetic waves travel with the same speed in vacuum, which is 300 million meters per second, or 3 times 10 to the power of 8 meters per second. Now, if v was the same for all, the change in frequency causes a change in wavelength. So a greater frequency, lower wavelength for the same speed. So that's how you can remember the relationship between frequency and wavelength for the waves in the electromagnetic spectrum. You must remember the waves in the sequence, and you must know which wave has the greater frequency and which wavelength, which has the greater wavelength. So just remember, from radio waves to gamma rays, increasing frequency, decreasing wavelength. Another way to help you visualize this as well is by thinking about the visualization of the wave. So you can see over here, okay, the wave frequency is increasing, so the waves are getting closer and closer and closer together. And in terms of the wavelength, the spacing between the crests is getting smaller and smaller. So greater frequency, smaller wavelength. Now the diagram on the top here is just showing us the non-ionizing and ionizing categories. This is not covered in this topic, but in case you're wondering, non-ionizing just means that these waves will not be ionizing air particles or other particles in general, whereas ionizing, the X-ray and gamma rays here will ionize other particles, especially air particles. You will learn more about ionizing radiation under the topic of radioactivity or atomic physics. So ionizing, because of the ionizing here means to force other particles to become ions, become positive and negative particles. So because these rays can ionize other particles, they are extremely harmful, whereas the non-ionizing ones tend to be they're okay, they're safe and beneficial when you use them in the appropriate dosage. The only difference here, though, is that for microwaves, they can be quite dangerous, and we will go into this in more detail when we cover microwaves in a few slides. So now, in the meantime, let us go through the applications and harmful effects of each of these individual waves. So yes, that's quite a bit. Now, before I move on, the following slides may seem like quite a bit because we're going through the application and harmful effects of each of these waves. My recommendation to you is you don't have to memorize all of them so much. Just use your logic to try to remember all the different applications and harmful effects, because these are waves that you should not be unfamiliar with. You would definitely have heard about each on and sorry, let me start that again. You should definitely have heard about each and every one of these waves some way or another, sometime or another in your daily life. So if you can take that application and that harmful effect and apply it into what you already know about what you are using in daily life, then you don't have to memorize so much. Cool? So what we're going to start off with first is radio waves. So some of the applications of radio waves include radio and television transmissions. Obviously, the term radio comes from the term radio waves, and radio waves are excellent when it comes to broadcasting and communications. So for example, when you're listening to the radio in your car or you're watching free television channels, that means the channels which you can watch using an aerial, you don't need to use satellite communications for that. Those are using radio waves for the broadcasting signals. Radio waves are also used in radio frequency identification, or RFID. So RFID is used by cards where they have chips with personal data stored in them. For example, your name or your contact information. So you can use your card as a personal identifier, which you can use, for example, to get access to certain restricted areas. These cards are very useful for people to get quick access to restricted areas where only certain people are allowed into. Radio waves are also used when it comes to studying astronomy, for example in radio telescopes which pick up radio waves emitted by celestial objects for astronomers to study and understand more about what lies out there. Radio waves are also used in Bluetooth communications, which is a short-range communication between devices, for example from phone to phone or even from phone to your wireless earsets. Bluetooth is also used to send files wirelessly between devices. These devices include laptops, tablets, and phones. So that's how you can easily send pictures between your phone to your friend's phone or documents from your laptop to your phone. So why are radio waves used so much in broadcasting? So for one, well, first of all, you need to know that electromagnetic waves, they're very useful as carrier waves. That means they can carry signals and information as they travel, so making it useful for broadcasting. So that means it carries the audio signals or the video signals that are used for radio and television, so for us to listen to, the music and to watch what's on TV. And why they're used so heavily in broadcasting is because of their very long wavelengths, which makes it easy for them to diffract around obstacles, as you can see in this diagram. So if let's say this is the Healy area, so the waves, because of the large wavelength, can easily travel around the obstacle and reach the recipient. Radio waves are very useful for short range communications. Right. Now, let's move on to microwaves. Now, because microwaves are actually high frequency radio waves, they're also useful when it comes to broadcasting, specifically for satellite communications. Microwaves are also used in mobile phone communications. That means the cell phones that you're using, yes, they use microwaves, which are basically high frequency radio waves. It also goes without saying that microwaves are used in microwave ovens, and microwaves are also used in wireless internet, also known as Wi-Fi connections. The danger of microwaves is that it can cause internal heating of body cells. So, how does it work? Now, microwaves are essentially high frequency radio waves. And remember, I mentioned just now, right? So, radio waves are able to carry information as they travel. So, microwaves can also carry information, and because of the higher frequency, they can carry more information. However, because they have higher frequency and shorter wavelength, they don't diffract as easily as radio waves. So that's why for microwaves, they need the use of satellites. Here is a slide to explain a bit more clearly. I realize now that my loom is blocking the text, so I'll move my face out of the way. All right. So over here, okay, here are some of the comparisons between satellite communication and radio wave communication. So for satellite communication, which uses microwaves, right? Some satellite phones use low orbit artificial satellites. So low orbit here means that, okay, satellites are in low orbit, right? And they revolve around 400 to 1,600 miles high, and they revolve around the Earth. So some satellite phones and direct broadcast satellite television use geostationary satellites. Geostationary satellites are much higher. They're about 22,282 miles high, and they rotate with the Earth. The term geostationary here means that geographically they appear stationary to Earth. So that means as Earth rotates, the satellite moves. Oops, where's my hand? It moves together with the rotation of the Earth. So although they're actually rotating, geographically they appear stationary. So that's why they call those kind of satellites geostationary satellites. So for those of you who are doing SPM, you would have learnt about geostationary satellites as part of your syllabus, right? So microwave ovens, right? And how they work? Okay, they microwaves. When you put the food into the microwave oven, among all the particles that are inside, what you put into the microwave oven. So for example, you've got your bowl, you've got your food, and you've got the water in there. So among all the particles, when the microwave reaches all those items there, okay, there will be some energy transferred to all of these particles. But among all of them, microwaves will cause the water particles to vibrate the most. So while all of them may vibrate, water particles vibrate the most. This kinetic energy will be converted to heat energy, which is then used to cook food. Now, of course, if you think about human body, okay, human body is made up of how much water? 60% water, right? So because the human body is made out of 60% water, this means that if we are overexposed to microwaves, overexposed here means we receive too much microwave radiation, right? If you get overexposed to microwaves, it can also cause this heating. That means the water particles in our body will then convert the kinetic energy to heat energy, and that's why this can cause internal heating of body cells. Does that mean that microwave ovens are dangerous to use? No, the manufacturers are not stupid. All right. They're obviously going to put in all the necessary shielding and protection to make sure that the appliance here is safe to use. That's why when you look at your microwave, there's always a little warning signal there, like say, okay, do not remove the cover. That's because there's a special cover there that prevents the microwaves from being able to come out of the microwave oven. So that's why the microwave oven can only operate when you have closed the door, firmly and shut firm. Then only the oven can start to work, right? Um, One way to test whether your microwave oven shield still works or not is by placing one of your mobile phones inside the oven. Don't switch on the oven. Just put the phone inside the oven. Close the door, use another mobile phone and try to call that mobile phone that's inside the microwave oven. If the shield works, then you'll find that the call cannot go through, right? And that's because the shield has prevented any electromagnetic waves from entering or exiting. That's why the signals cannot be found. If you find that you can call the phone in there, then maybe it's time to change your oven because the shield no longer works. Okay, moving on. Okay, so I put a space here for my face, but I realized there's not enough space for the recording button. Oops. Okay. Am I moving on? So radio waves versus microwaves. Now, the difference here is this. Both radio waves and microwaves are used for broadcasting and for communications. And remember, microwaves are just quite essentially high frequency radio waves. The main difference here is that radio waves have much higher wavelengths, while microwaves have much higher frequencies. So in our atmosphere, the ionosphere is made up of charged particles. And what happens is that when the radio waves travel out, the charged particles in the ionosphere will cause the radio waves to reflect back to Earth. So that's why they're so useful for local broadcasting and local transmissions. You don't really need a lot of what I call, you do need some relay stations to be able to relay the signals further. But if you're looking at an immediate area, they're actually quite useful. They're quite good at being able to transmit information within a local area. So that's why radio waves are useful for local broadcasting. As written here, radio waves are useful for local broadcasting. Microwaves, on the other hand, let me move my face back. Microwaves, on the other hand, because of the very high frequencies, can penetrate the atmosphere easily. So that's why we need to use satellites. So microwaves, unlike radio waves, cannot reflect back onto the surface of the ground. So in order for microwaves to be used for communications, we need a satellite. So how it works is the transmitter will send a signal to the satellite, and the satellite would then send the information to each individual receiver. So if you have a satellite television at home, for example, that's why every home needs a satellite dish. So every satellite dish will be receiving the signals individually from the satellite. So that's why each home or each unit, each phone needs to have its own little satellite dish to pick up the satellite transmission, the microwave from the satellite. So microwaves or satellite communication they're very, very useful in larger areas. So that's why previously, I think even until now, when you look at ships that are out in the middle of the ocean, when you don't have relay stations, you can't use normal mobile phones. That's why you have to use satellite communication, because the satellites can send the signals directly from the satellite onto your ship that is, in middle of nowhere. Let's move on now to infrared. Let me move my face here. So for infrared, now infrared applications include the electric grill, short range communications such as remote controllers for televisions, also aircon, right? Intruder alarms, thermal imaging, optical fibers, and motion sensors. Generally, how do they work? So for infrared radiation, okay, infrared radiation, if you recall, right, it's a method of thermal energy transfer. If you remember, there are three ways of energy transfer. You've got conduction, convection, and radiation. Radiation is transmitted basically or transferred through infrared. Infrared radiation is emitted by all hot objects. So just like radio waves and microwaves, right? Infrared radiation is also able to carry signals. However, it must travel in a straight line because it does not diffract easily due to its very, very short wavelength. So straight line only. That's why when you use your remote controls, you have to point the remote control at the receiver directly. If you're pointing it anywhere else, if you're lucky, it might get there because of reflection, but otherwise cannot because it must travel in a straight line. And that also makes it very useful actually to be used in optic fibers. So we use infrared to carry the information, and because it travels so quickly, that's why we use it as in our high-speed internet broadband. We use optical fiber for that because such high speed. And when light travels, as it carries information, it doesn't go out of the optical fiber, even though the fiber bends because of the concept of total internal reflection. So this is covered under the light topic. If you don't recall anything about this, then please watch my video on total internal reflection. In the meantime, let's move on. So, wanted to show here. Okay, let me put my face somewhere here first. All right, so infrared motion sensors and how the sensors work. They work by detecting the changes of infrared radiation within the area of detection. And now, human beings, of course, we do release infrared radiation, but very, very low levels. These sensors are so sensitive they can detect these very low levels, and that's how it detects. Oh, there's something there that's moving. Ping, right? So you find that infrared motion sensors, they're used, for example, in automatic doors. So that's how when you walk in front of the door, ching, can open like magic, right? Yeah, because of the infrared motion sensors. One of my students did ask, but what if it's on a very hot day? Now, remember, the infrared motion sensors detect the changes of the infrared radiation. So if it's a hot day, everywhere is pretty much hot. But if someone comes along, it becomes even hotter, right? So then she says, oh, something's there. Ding, right? And depending on the sensors, how it's calibrated. So sometimes they will only open when there is enough of this there's a significant change. So that means that instead of one hot ball, a tiny ball rolling there, like, okay, too small, okay, that's not a human being. So you got to have at least maybe a child size infrared radiation detected. Oh, big enough, ding, door open. So it's possible. So it depends on how the sensor is calibrated. So maybe it's got to be like large enough before it triggers. So before we move on to the next electromagnetic wave, we're just going to do a quick comparison between some of the different electromagnetic waves which are used in communications technology. As already mentioned in an earlier slide, mobile phones and wireless internet use microwaves. Now, the reason that they use microwaves is because microwaves can penetrate some walls and only require a short aerial for transmission and reception. Bluetooth, on the other hand, uses radio waves because radio waves can pass through walls. However, you should be aware that the signal is weakened when they pass through the walls. Now, for optical fibers, they use visible light or infrared for cable television and high-speed broadband. So optical fibers are made of glass, and glass is transparent to visible light and some infrared. You should be aware that visible light and short wavelength infrared can carry high rates of data. Now, if you are wondering how is it possible that light is able to carry data, here's what you should understand about electromagnetic waves. Because of their very nature of consisting of electrical and magnetic fields, the electromagnetic waves can actually carry data. That's why microwaves, radio waves, as well as visible light and infrared are able to carry data. So they're data carriers, meaning that this data is encoded into these waves. So as these waves are transmitted, they carry the data with them. So normally when they're transmitted, the data has to be encoded into these electromagnetic waves, and then when they reach the receiver has a decoder which decodes the data from the carrier wave in order for us to be able to make sense of the data. The data here can include things like audio, which is used in radio communications, audio and video, which is what is used in television communications, or it can be other forms of data, for example, internet connections. Okay, moving on, visible light. Okay, so just to show you here, okay, now remember that for visible light means that it's the light that human beings can see. In the entire electromagnetic spectrum, the visible light spectrum is the only part of the electromagnetic spectrum that human beings can see. So that's why we call it the visible light. So the visible light part is made up of the light spectrum of the rainbow colors, the Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And also, yes, you need to know the colors in that correct sequence, right? From this like from red, okay, to violet, right? You need to know the color in sequence. Okay, this is the only part which human beings can see, and therefore it's used for vision, for photography, and for illumination. Moving on, ultraviolet light. Now, ultraviolet rays are used for insecurity markings to detect fake banknotes and also used for sterilization, for example, sterilizing water. The dangers here, of course, because of the extremely high frequencies bordering on ionizing, they're not quite ionizing yet, but almost there. The very high frequency can cause damage to surface cells and eyes, leading to skin cancer and eye conditions. How does UV work? So, for UV, okay, right, how it works is that now a special ink that cannot be seen under normal light, but they can reflect ultraviolet light. We use them in as security markings as well as on authentic currency. So these markings can only be seen when we shine ultraviolet light on them. So that's why they show up. So under normal light, you can't see anything, but you shine, there you can see the writing, or you can see the ink on the authentic currency. That's how we use them as security markings. Similarly, this is also how stains are detected in forensic science. Because certain stains, like blood stains, for example, even though after you've cleaned off the blood, but there's still some staining there. Although we can't see them, with normal eyesight, you can't see them under normal light. But when you shine UV light, the the what do you call the cleaned up area, there's still some staining there, can reflect the UV light, and that's how they show up under what you always hear them call as black light. So it's not really black, it's actually UV light. They call it black because when you shine, you see there's no light there. Yeah, because you can't see UV lights, but you can see the effect of that ink or the stains reflecting the light. That's why I call it black light. Okay, it's not black, it's ultraviolet. Okay, so ultraviolet ultraviolet radiation, as we know, also has a very high frequency. So this high frequency is able to kill virus and bacteria by targeting their proteins and breaking down their DNA and RNA. So it makes it very suitable for sterilizing water and air as well as other personal items. So some of you may have water sterilizers at home that have the ultraviolet treatment. So that's why it's safe to drink directly from the tap if you have the UV sterilizer with a filter, because in terms of all the microorganisms, the UV radiation have already killed most of them, right? And that's why they're also useful for sterilizing personal items. You might find that some of the baby item sterilizers use UV to make sure that they kill off all like as many microorganisms as possible from the like baby bottles and all that, to make sure that they're clean for the babies to use. But also because they can kill cells, they can also kill normal, healthy living cells, right? So that's why overexposure to ultraviolet radiation can cause skin cancer and eye damage. So people who love to suntan or go to the tanning beds, right? UV is what makes the skin color turn dark. So yes, for your skin tanning, you need to expose yourself to ultraviolet rays, but overexposure can also cause skin damage and skin cancer. So a word of warning. All right, moving on. X-rays. All right, so X-rays are used for medical scanning and security scanners, as you should know. So if any of you ever had broken bones, or if you have to get braces done, you know you'd have to take X-rays. So X-rays are used for medical imaging purposes. And those of you who have traveled before, you'd have to put your bags through the security scanner. And there's basically an X-ray machine that allows the airport security to observe what's in your bag without opening your bag. Like faster privacy is not really violated in this case, right? Yeah, right. Good job. Now, of course, X-rays, because they're now on the higher end, high frequency end of the electromagnetic spectrum, again, can cause a lot of damage to living cells. So yes, the danger here: mutation or damage to cells in the body. So X-rays are usually able to penetrate soft tissue, but it's typically stopped by dense material such as bone. So how X-rays work is, okay, for example, you look at this diagram. So this patient here is having an X-ray taken of his arm. So we've got an X-ray generator here that will shine the X-rays. The X-rays will travel through the patient's arm. The X-ray film is placed underneath the arm. So the X-rays can penetrate the soft tissue, but it's stopped by the patient's bones. So what happens is when the X-rays reach the film, they will react the film and turn the film black. The part of the film which the X-ray cannot reach will stay maybe like white in color, for example. So that's why on the film you see, okay, the black color area is where the X-rays have reached because it can penetrate the skin or just travel around in the air. So the part that gets blocked is the bone. So that's why the bone shows up. And that's why the film is able to show the bones. So if any of you have taken, X-rays, you don't have to be lying down. You could be standing up. Just the film is behind you. The X-ray machine is in front of you. It works exactly the same way. But this is also why when we want to take X-rays, we have to take off jewelry because metals can also stop X-rays. This, in a similar way to how bones can stop the X-rays because they're also quite dense. So that's why if you wear a necklace, the necklace shape is going to show up in the X-ray. And if you like to look up some of these cases, there's been past cases where when doctors look at the X-ray, they thought there was something stuck inside the patient's body because of the X-ray, and it turned out after surgery and all they couldn't find it. It turned out it was because the patient wore jewelry, forgot to take out, when they were taking the X-ray. So that's why if you're taking X-rays, have all your jewelry removed. Just wear only the fabric apron which they ask you to wear, so that you don't have accidental surgery trying to remove something that's not there. Moving on, gamma rays, because they're on a much higher like frequency end, right? So they're the highest frequency of the electromagnetic spectrum, right? They're used for sterilizing food and medical equipment, and also good for detection of cancer and its treatment. And similar to X-rays, they can cause mutation or damage to cells in the body. And why? They're used for sterilization because of the high frequency. So gamma rays at low levels can kill many microorganisms such as bacteria, viruses, and fungi without changing the chemical components of the food. And this can be very useful in removing harmful microorganisms from food and makes the food last longer. So one way which gamma rays are used as sterilization of food is, you can see here, they have the food all packaged in boxes and in tins and all that, all sealed already. So what happens is they will just pass the boxes under the gamma radiation machine. So the gamma radiation can pass through the packaging, and they kill all the microorganisms that are inside the packages. But because the packages are sealed, no new microorganisms can come in, and that allows the food to stay fresher for longer. Now, even without packaging, we have also used gamma radiation to keep fresh food longer. So even without packaging, this still works. Like for example, the strawberries, we shine very low levels of gamma rays. So the levels are so low that they don't change the chemical composition of the strawberry, but it can kill the bacteria inside. So now remember, what makes food rotten is the presence of all these microorganisms. So by getting rid of all these microorganisms, the food can stay fresher for a long time. And that's why we can get imported fruits that seem fresh, even though they've been, in transit for, like a couple of weeks, for example. Wonders of technology, right? Yeah. Also, in terms of equipment sterilization, right? Because again, the high frequency able to kill the bacteria, the viruses, bacteria, and spores. So by placing the utensils in a sealed container, right? We place all these utensils in this sealed container, put it into a machine called the autoclave, which basically shines gamma radiation onto the equipment. So just like with the food explanation just now, So all the microorganisms that are trapped inside have been killed by the gamma radiation, but because they're sealed, no new microorganisms can enter. So this is wonderful, especially for surgery, because you don't want a situation where the doctor's doing surgery and accidentally introduces bacteria that were not there in the first place because the utensils were not clean to begin with. So this is a method that they found that has been so amazing. That's great for surgery because completely clean. There's no microorganisms, so surgery can be conducted safely. Gamma radiation is also used for radiotherapy. So because gamma rays, high frequency again, right? Not only can kill microorganisms, can also kill cells. So they can kill um, like basically cancer cells, for example. So they can kill the cells or slow their growth. So cancer treatment is done by targeting the gamma radiation onto cancer cells. This is an example of how gamma radiation can be used to target brain tumor. So the patient's head is enclosed in a helmet device, and this device focuses narrow beams of gamma radiation towards the tumor in the brain. Now remember that gamma radiation does not only kill targeted cells, it basically can kill all cells. That means all the living cells, all the healthy cells that are in the way may also be exposed to the gamma radiation. So that's why we need to set it up this way. So the levels are low enough that they won't kill. So the cells that have been exposed may just be slightly damaged, but they can still recover from the exposure to gamma radiation. But we target it in such a way, target the tumor in such a way, because they're all being targeted, then the tumor receives the highest level of exposure, enabling the treatment to be done and focused on the tumor. So the tumor cells can be killed or the growth can be slowed. And that concludes this topic. So I'm going to move my face a bit here. All right, so if you have found this video to be educational and helpful, please remember to click like and subscribe for more videos from your teacher, Miss Ho. Right, so thank you for watching and happy studying.